Okay, so we've finally finished like most of the prerequisites for now. Um, as I was studying on my own, I realized that there's a bunch of other stuff in terms of prerequisite knowledge um, that I might want to cover. Um, but we'll see, like we'll talk about that when we get there. Um, just to give you an idea of what those things are, it's about spin. So if you've heard about the spin in quantum mechanics. It's somewhat of a generalization of this idea. Um, but yeah, to discuss it the way I want to discuss it, there's some algebraic prerequisites um, that are still missing. Um, but I don't know, depending on if we even get there, I'll see what to do about it. Um, but yeah, okay, so before we even start the meeting, like the actual discussion of the content. Um, I do want to spend a little time on sort of planning out the next couple of meetings because this is also technically part of the prerequisites. However, it's a different it has a different quality to it because we're now like starting to talk about the geometry part of um like we finished the main prerequisites I wanted to get through. Now we're talking about the geometry stuff. So we're setting up the stage to be able to talk about physics, um, or rather to describe physics. Um, so the way I want to the way I want to do this now is in classical physics, we do all our work on these objects called manifolds, which will be the bulk of the discussion today. Okay, so we will describe what this object is. Um, I mean, in physics, we mainly talk about smooth types of manifolds. We'll also talk about other types of manifolds very briefly because we have no use for them right now. So things like complex manifolds, Banach manifolds, stuff like that. Um, so we have this, and now this is like this is like the main stage, and now we have to use the ideas of manifold theory to describe physics. And one of the main things we'll talk about are um, these objects called fiber bundles. I'm not sure if fiber is spelled like this or with RE in math. I've seen both spellings, so I'll stick with this one. So we'll talk about fiber bundles. So fiber bundles will cover things like the tangent bundle, so we can talk about vector fields. So things like um, tangent bundle, cotangent bundle, like tensor bundles, um, etc. Um, and the idea of fiber bundles are extremely important in physics. Um, when we're talking about things like gauge theory, we'll see that we have actually a little more structure to a fiber bundle, but the underlying idea is still that of a fiber bundle. Um, we'll then we'll then talk about Lie groups. Okay, we'll talk about Lie groups. So essentially, a Lie group um, is a group that is also a manifold. And then there's some like compatibility criteria with multiplication and inversion being smooth and whatnot. Um, but we saw already that group actions are extremely important when we're just, dealing with everyday objects. Um, and so a good formalism for talking about group actions on smooth manifolds would be to have the idea of a smooth group action, right? So we can, talk about group action and then use the theory of group actions to, talk about our space. Um, and then we're going to use the ideas from Lie groups to develop the concept of a principal G bundle, okay, which is a fiber bundle that has a group action on it. Don't worry about what a fiber bundle is, but for now, we can just um, take that. So this is the this is everything we need to set the stage. Okay, this is everything we need to set the stage. And now, after this, what we're going to do is we're going to shift our attention a little bit, and we're going to talk about Riemannian manifolds. So these are manifolds, whatever these objects are, with the notion of a distance almost. Okay. They're not quite distances. I mean, they are, but they aren't. So we'll talk about Riemannian. But in physics, we actually almost never have a Riemannian manifold. So what we'll at some point start talking about pseudo-Riemannian. I feel like I'm misspelling that. There should be an E in there somewhere. Um,
Before the
before the U? Yeah, okay. Okay, so yeah, we're gonna talk about pseudo-Riemannian manifolds, which are we'll see when we get there, but um general relativity happens on pseudo-Riemannian manifolds. So the notion of general relativity requires something stronger than the idea of a manifold. Um, our underlying space um, is a manifold, but to do physics, we'll see that we require additional like objects on these um, spaces. We'll then talk about connections. And we'll talk about connections on like fiber bundles in general, and then we'll specify to the case of, well, not fiber bundles, on vector bundles, which are a type of fiber bundle. Um, and then we'll specify to the case of principal connections and like connections on principal bundles. Um, and then we'll also talk about curvature, torsion. Um, it turns out that in physics we ignore torsion. Um, we ignore torsion because torsion makes everything very bad. Um, so everything we will do will be torsion free. Um, well, not everything. Again, I'll see how things are going, and then we may or may not talk about torsion. I know, I mean, I will introduce the idea of it of torsion, but um, I'll see whether we want to like go in depth on the theory of torsion. So okay, we have curvature, torsion. Um, I think that's it for the Riemannian section. So Riemannian manifolds um, are now like setting up the props. Okay. You have the stage, which is the manifold, and now you have the props, which is the Riemannian structure. Um, and then now we have to use these structures to do physics. So we need the actor. Okay. And the actor in this case is going to be the symplectic manifold. Okay. So once we've talked about like here's how you measure distances, here's how you measure curvature, um, here's how you know, rotate something in a manifold, here's how you give an action of something. Once we have all these ideas, we can combine all of them and use the ideas from symplectic geometry to do physics. Okay. We'll see that symplectic geometry will very naturally give rise to Hamiltonian mechanics. Um, and we may talk about fibrate like this the notion of a fibration. Okay. I'm putting a star here because I don't know how relevant that might be. Okay. Once we have all of this, like, if you've done any like um theoretical classical mechanics, you might know that there's two main ways to talk about classical mechanics. Those are the Lagrangian formalism, and the other one is the Hamiltonian formalism. Symplectic manifolds naturally give rise to the Hamiltonian side of things. So what about the Lagrangian? As it turned out, the Lagrangian side of things are more naturally described when we talk about the tangent bundle. So way up here, you don't need all this. Um, but I'll save the Lagrangian stuff like till after we talk about the Hamiltonian. Because um I think in some sense the Hamiltonian formalism is a little more um I don't know, because both of them are very like if you follow this progression, you'll see that both of the ideas are very not intuitive, but once you've seen it, you will think that it is an intuitive thing to do. But setting up Lagrangian mechanics is a little unintuitive. So then we'll talk about Lagrangian mechanics like at the end. Okay. Um, okay, so this is the main structure that I'm hopefully trying to get through by the end of next semester. Um, and if need be, we can, of course, continue into the summer and stuff. Um, some things that I may cover if we get the time is the notion of spin. Um, and well, spinners and spin geometry, geometry. Um, spinners naturally arrive in quantum mechanics through stuff like the Dirac equation. Um, and so the Dirac equation is sort of a relativistic cousin of the Schrodinger equation. Um, and it naturally describes like spin one half particles. Okay. Okay. Uh, so spin and spin geometry. Another thing we might talk about is Poisson geometry. Okay. We may see this, we may not. I don't know, depending on how much time we have and like if people want to continue into the summer. But okay, with all of this out of the way, are there any questions about things you were hoping to see that is not clear that I might talk about? No, we're good. Okay. So with that out of the way, let's now talk about manifolds. Okay. So if you remember when we talked about topology, um, I introduced the notion of this topological object um, that behaved similarly to flat space. Not in every aspect, but locally at least, it was flat space. And I use the word flat very lightly. And when I mean flat, I mean it looks like Euclidean space. Okay. And just to remind you, we defined the idea of a topological manifold to be the following. Okay. So a topological space X is a topological manifold if one, it is Hausdorff or T2, whichever one you prefer. If you remember, Hausdorff just means for any two distinct points, we can find open sets containing each of the points that don't intersect. Um, so, so I mean, okay. Um, there these like T axioms, they're called separation axioms. There's a bunch of them. There's like T0, T1, T2. There's T3, T3 and a half, T4. I think that's where it stops. I'm not too sure though. But these are the separation axioms because they talk about how like how much can you separate like how much can you separate two objects like within your set by like whatever. Another thing is we require this to be second countable. If you remember, if you recall, second countability um, just means that there's a countable basis for the topology. And if you remember, a basis is something that generates the topology in with like one additional property. And the third one, which is the most fundamental property, is that for every P in X, there is an open neighborhood U in X, okay, and a homeomorphism phi from U into some open set in Rn. Okay. This is what gives this is what gives manifolds their local Euclidean property. It's the fact that locally they behave as if they were subsets of Rn. Okay. Note that there's nothing sorry, note that these might like this the topological space X might not be a subset of Euclidean space inherently. Okay. Um, and that's one thing to keep in mind. Like uh, there is a theorem in the case of smooth manifolds that says that every smooth manifold can be embedded into Euclidean space, right? So we can at some point we can treat every manifold as if it was a subset of Euclidean space. But the idea is that we don't want to think about it that way. Okay, we want to think about the manifold on its own. Okay, it's its own object. It's its own object. Right? Okay, so just some quick examples. So Rn is a manifold, a topological manifold. Right? I hope this is clear to see, um, because this property is the only non-trivial one, but you know, you can just pick U to equal Rn and phi to be the identity map, and you'll get a homeomorphism. I just realized I forgot to mention one thing. Um, the pair U phi, okay, so the open set U and the map phi is called a chart. Okay, it's called a chart. Let me write that slightly nicer. Okay. The reason we'll see that everything in manifold theory has names that might remind you of things in maps. Um, when I mean map, I mean like a map of the Earth, for example. Like that's the type of map I'm talking about. And that's because one of the pioneers for manifold theory, well, classical manifold theory, was Gauss. And Gauss was a cartographer by trade. So he was mainly interested in how can I make a map of the Earth? That was his main idea, right? How can I make a very good map of the Earth that doesn't distort things the way regular maps do? And what he realizes that you can't do that. You cannot create a map of the Earth that doesn't distort something. And that has something to do with the fact that the Earth is curved, right? Has some curvature to it, but a map doesn't. A map is not curved. Okay. So yeah, Rn is a manifold. Um, Another example of a manifold is like Sn, which is the set of points x0 up to xn and Rn plus 1, such that the sum of xi squared is equal to 1. This is a manifold. Um, One can show that this is a manifold using this definition. But as we'll see, it's very hard to do that. I mean, it's not very hard. It's just very tedious. Um, so we'll come up with a technique that I'll present next meeting, um, to show that this is a manifold. One more thing to note is that the set of matrices, like matrices in Rn, is a manifold. The general linear group of R is a manifold. The special linear group is a manifold. The special the unitary group, the special unitary group, the orthogonal group, the special orthogonal group. All of these are examples of manifolds. Okay, they're all manifolds. So in some sense, like we have a huge class of manifolds. We'll show all of these are manifolds. We'll show, like, including this one, we'll show using something called the regular uh, level set theorem. But we'll get there when we get there. Okay. But for now, just take my word for it that these are manifolds. Okay. Are there any questions on what a manifold is? Okay. Are we happy with this definition? Are we happy with the examples? Okay. So topological manifolds, okay, there's more definitions. So um if we take um if we take the collection of charts, um collections of collection of charts, how do I want to word this? Um okay, let me actually just go in. So an atlas for a manifold is the collection um of all charts on that manifold. Okay. So what I mean by that is, like, you have one point, there are a bunch of charts on that, like at that point. So you take all those, then you go to another point and you say, okay, there's a bunch of these charts, so we take those charts as well. And then you do that at every point. So you just take every chart at every point. Okay. And the collection of all these charts gives you an atlas. Okay. Again, map name, map terminology. So, okay. Um, given given charts U phi and V psi, the maps phi inverse composed with psi and psi inverse composed with phi are called transition maps. And the reason they're called transition maps is because, well, they transition you from one chart to another. To see why this is the case, let's look at the domains and ranges of these maps. So if we note that phi goes from u into like u hat, psi goes from um, let me actually do it this way. So u into u hat, v into v hat. So psi goes like this, phi goes like this. Now psi inverse goes like this, and phi inverse comes like this, right? So what this means is that if we compose with psi, and then phi inverse, we're going this way, we're going up somehow, and then we're coming over. So then we get a map from u to like v to u, right? And then similarly, if you have psi inverse, so you first do phi, you somehow come down, and then you come back, so then you get a map like this. Okay. So you need that like u and v intersect. Otherwise, these maps are like empty. Um, okay, are there any questions about transition maps? Like, is there any question on like the definition of a transition map? Okay. Now, now there's nothing specific, like there's nothing special about Rn. Okay. Um, so we could have charts um that map us map us into Cn, for example, or X, where X is a Banach space, right? There's nothing special about Rn, right? Um, so in the case that the chart maps us into Rn, we say that it is a real topological manifold. In if phi is from U into U hat, which is a subset of Cn, then X is okay. I chose really bad. Let me say that this is M. Okay. Um, then M is a complex um, manifold. If phi maps you into some Banach space X, then M is a Banach manifold. Okay. But now the category of like real manifolds or real topological manifolds is, I don't know. I mean, you can have a bunch of weird things happening, right? For example, you could have a cone that has a singularity um, at a point, right? And if you're if you're doing like theoretical physics, singularities like this, at least in the classical case, they're not that nice. When you talk about quantum systems and stuff like that, then you can introduce singularities because, for example, general relativity at small scales does produce singularities. So then you're forced to deal with singularities. But when we're talking about the classical case, we can just pretend like singularities shouldn't exist, right? So we somehow need to smoothen out um, the definition of this like of manifolds. Um, and to do this, what we're going to do is we're going to introduce the idea of a smooth manifold. So a smooth manifold. Okay, so let's make a heading here. Smooth manifold. Okay. So the way we're going to define a smooth manifold is we're going to look at these transition maps, okay? And then we're going to ask ourselves, what do we know about transition maps? Okay. I also realize I have the directions here incorrect. Let's, sorry, my bad. Uh, the inverses happen on the first map, not the second. Sorry about that. So if you look at it, transition maps go from our maps from open subsets of Rn into open subsets of Rn, right? Transition maps are open subsets from Rn to Rn. So what this means now is that we can talk about whether this map is smooth. We've talked about with the idea of differentiability on Rn. So we can now ask if these are smooth. Okay. So um, if U, V, and V psi are charts with um, phi compose psi inverse and psi compose phi inverse both smooth, then the charts are said to be C infinity compatible. Okay. Because they're compatible, like they're smoothly compatible with each other. The transition is smooth. Yeah. Okay, is there any question about this definition? Because this is one of the most central ideas in all of smooth manifolds. This is a very, very, very important definition. C infinity compatible. So are there any questions?
This is just smooth in the like normal sense, like the derivative sense, right?
Yeah. So we have maps between Rn and Rn, and then we talk about whether those maps are smooth or infinitely differentiable. Um, yeah. Okay. Again, there's nothing specific, like there's nothing special about smooth maps, right? Like we could have any collection of maps. For example, if you wanted analytic maps, you could impose that the charts are analytic. Okay. If you wanted the maps to be continuous, you could impose um, that the transition maps are continuous. In that case, all you would get is a topological manifold. Okay. Okay. Now, what we're gonna do is um, we define a smooth structure on a topological manifold M. I'll subdue the topology because that's not really important. We define a smooth structure on a topological manifold M to be a maximal C infinity compatible atlas on it. Okay. What do I mean by this? So let's start with what a C infinity compatible atlas is. So you take an atlas and it's C infinity compatible if any two maps you pick are C infinity compatible. Okay. Is that okay? It's maximal if we take the largest such collection. Okay. Um, one can actually now show that this maximal C infinity compatible is completely determined by one atlas that is below it. Um, in the case of Rn, you can pick one map and you can get a smooth structure. Uh, a smooth structure is determined by this one map. Yeah. So, so okay, do we understand what the definition of a smooth structure is? Okay. It's just the largest collection of C infinity compatible maps you can like fit together. Okay. Now, in some sense, this collection is much, much, much smaller than the collection of like the atlas in the case of a topological manifold. Okay. I think this idea is so important that I'll actually give an example. Okay. So example. So say you have R, okay, and you wanted to determine a smooth structure on R. Okay. Note that the identity map from R to R is a homeomorphism, right? And the map f of x, the map f from R to R, given by x goes to like the cube root of x. Both of these are homeomorphisms, but but they are not they are not C infinity compatible. Why is this? Because if you take f composed identity inverse, this is just f of x. Um, but f of x equals this is not smooth at zero. So even though the transition map is continuous, okay, even though the transition map is continuous, the um it is not smooth. Okay, so in the topological atlas, both these maps would sit together, but in a smooth structure, these two maps cannot coexist. Okay, you have to pick either the first or the second. Okay, so what this tells you now actually is that if I pick this map to be in my atlas, I get like I get a smooth structure that is completely determined by this guy. Okay. It also turns out that this thing over here, like this map over here, also determines a smooth structure. I will outline the proof of that in a problem sheet because I think it's a very fun exercise. Um, I think if you sort of um, if you work through this exercise, I think it'll give you the main insight you need. Um, I think it'll give you a lot of confidence in working with manifolds because this is sort of like this is one of the many like hurdles that come up in trying to understand manifold theory. It's that even though like two things feel like they should be part of the same chart, sorry, same smooth structure, they're not. Okay. Does this example like highlight what the definition of C infinity compatible and the definition of a smooth atlas is? Like, are we happy with this? Okay. Okay. Very good. Now, one more thing to note. Note, however, that if you take like the identity map and f from R removed 0 into R, remove 0, given by x goes to the cube root of x, then f, let me call this g just to avoid confusion. Then ID and G are C infinity compatible. And the reason for that is we've removed the trouble point 0, right? So we've removed the trouble point 0. The cube root of x is smooth everywhere other than 0. right? And we've removed the like issue point. Okay. Are there any questions on like this fact? Because I think this is so one thing I would urge you to do is check that G is a chart. So check this. And then convince yourself that like they are C infinity compatible. If there's no questions, I'll move on. A smooth manifold is a topological manifold M with a smooth structure. Okay. It is a topological manifold with some assigned smooth structure. An example of this is R with like Rn with the chart R I like the identity map. Like as we talked about chart, um, this chart determines a smooth atlas. Um, Another example is R with the chart R and F. This gives you another smooth atlas. Sorry, smooth structure. And these smooth, like this smooth structure and this smooth structure are not the same. Because if they were the same, then every map would be C infinity compatible, right? But they're not, as we saw here. So this and this are two different smooth structures on R. Okay. It's similar to how in topology you can have one set with many different topologies on it, right? Some might be homeomorphic to some other one, but not every topology on a set is the same. Yeah. Um, we'll see that Sn um, is a smooth manifold. And you might now complain that I haven't given you charts. Um, and that's fine because if you want here, I'm taking the charts determined by something called stereographic projection. Now, stereographic projection to write down mathematically is extremely annoying, so I'm not going to do it. But I urge you to look it up. Lee's Smooth Manifold textbook does talk about the stereographic projection in pretty good detail. So if you're interested, please go through Lee. We'll show that Sn is a smooth manifold with like the standard structure using the regular level set theorem. Because I think it's just easier that way. Um, but yeah, all the matrix groups above are smooth manifolds. Manifolds with the standard charts. By standard charts here, I mean like they're all subsets of Rn. So you take charts and you restrict them. Okay. One sort of interesting example is Cn is a smooth manifold, is a smooth manifold. Um, and here, like determined by 5 of z1 up to zn equal x1, y1, xn, yn, where zi is xi plus I, yi. Okay, let me know I use I. I didn't think this through. Okay, so if you write complex numbers like this, you get a chart. Okay, are there any questions about these manifolds? let's continue. Um, let's now talk about the dimension of a manifold. I was sort of skeptical defining this because even though it's a very central idea, it is a little hard to justify the definition. Um, so 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 let M be a smooth manifold, with its like at like smooth structure and whatnot. I'm not gonna write that down. M be a smooth manifold. Then M is said to be M dimensional if all charts have codomain in Rm. Okay. So all charts have like their codomains is in Rn. So like if we go up to the definition of a chart, like this is the same for every point. Okay. Um, Now one thing to note is that Rn and Rm, so note, this is a well-defined definition because so Rn and Rm are isomorphic if and only if n is equal to m. Okay? And the proof of this can be done using something called homology. But I won't get into homology. I think um, this is sometimes called the invariance of domain. Um, but yeah. Okay. So the dimension of a manifold is only well defined if it's like the same at every point. You could have like okay, let me give you a pictorial example of where dimension doesn't make sense. So you could have something that looks like this, oh, like this, with this point over here. Like this collection is a manifold. However, the dimension here is 2, but the dimension here is 0. Okay. So in this case, it doesn't really make sense to talk about the dimension of this manifold, even though it is a manifold. Okay. Um, Another example is like you could have something like this. In this case, it does make sense to talk about the dimension of this manifold because at each point the dimension is 2. So here the dimension is 2, here the dimension is 2, here the dimension is 2. Okay. So at every point it makes sense to talk about the dimension. So here we cannot talk about dimension, here we can talk about dimension. That's why I was a little skeptical. But from now on, we will talk about manifolds with dimension. Okay. So at each point they have the exact same dimension. Okay. So let's just give the dimension of some of the manifolds. So um, I hope it's clear that Rn has n dimensions because that would be a very unfortunate naming otherwise. Sn has n minus 1 dimensions. And this makes sense because if we look at the circle, this is S1. So yeah, misspoke. Sn, the dimension of Sn is n. Okay. And I hope you can make sense of this because in some sense, you have n plus 1 coordinates, right? But you have this one constraint. I can reorganize this constraint to solve for one of the coordinates using the implicit function theorem, right? So we somehow remove one dimension because one of the coordinates is determined by all of the others, right? So using the implicit function theorem, I hope it's at least intuitive to see that Sn has n dimensions, okay, as a smooth manifold. Um, GLNR is an open subset of Rn squared, which means it has the same dimension. Okay, it has the same dimensionality. Okay, so this also has dimension n squared. The special linear group also has one constraint, which is that the determinant um, is that the determinant equals 1, right? This is one constraint. So this has n squared minus 1 dimensions. Does that make sense? So that's how you sort of count the dimension of this manifold. Like you look at the number of constraints it took, you take whatever space you had initially, and then you subtract off those, um, like subtract off that number. Okay. So we briefly mentioned like category theory, and in category theory, we saw that okay, when we introduce a new mathematical object, we want to talk about maps between those objects. So what is the map between smooth manifolds, right? Um, okay, see you, man. Bye-bye.
Thank you.
Yeah, so when we talked about category theory, we saw that whenever we introduced a new object, we also talked about maps between those objects, right? So in the case of smooth manifolds, what should these maps be? And I hope it's clear, at least in terms of naming, that it should be smooth maps. Okay. Maps between smooth manifolds should be, well, let me actually call maps in the category of smooth manifolds should be smooth. What do I mean by now? What does it mean for a map between manifolds to be smooth? So suppose that F is a map from one manifold into another. What does it mean for this map to be smooth? Um, this is smooth at P and M if there is a chart. There's a chart U phi around P and a chart V psi around F of P such that the map. So okay, when we talked about transition maps, right, and we imposed that transition maps should be smooth. And the reason we could talk about smoothness there is because we had maps between Rn and Rm. Okay. So we somehow want to make F into a map between open sets in Rn. Um, and just for notation, I'm gonna put an M here to mean the dimension and N here to mean the dimension. So this is dimension. This is not how many copies of N. This is that M is M dimensional and N is N dimensional. So I don't have to keep writing that. So we want to somehow make F into a map between we want to make F into a map between open sets of Euclidean space. Um, and to do this, we're gonna take F, we're gonna pull it back using the inverse of a map, and then we're gonna push it forward using another map. So let's see. So want to start um, we want to start in the open set um, around the point P, but its image by the chart. So we want to start in Rm. So we have to use the map phi inverse because now we're in Rm. We have to come back to M. To come back to M, we have to use the inverse. Now we can compose this with F, right? So now we're in N. And then we have to go into Rn. So we have to compose by psi. Okay. So we can talk about this map. Okay. And then we just say F is smooth at a point if this map is smooth. Okay. Now one thing to note that if F is smooth, let me actually just finish the definition. F is smooth if F is smooth at all points. Yep. very, I love definitions like this. Um, okay, now one thing to note is that if f is smooth, then um, it doesn't, the choice of chart doesn't matter. Choice of chart does not matter. And to see this, suppose you, um, so suppose like you have charts like this, okay? U and U prime, these are charts around P, and suppose that F is smooth in this chart, okay, in the first chart, and V psi and V prime psi prime charts around F of P, right? And it's smooth in this chart, then we now show that it's smooth in this chart and this chart. To do that, it's just composing like a bunch of things. So note, so we have, well, we have psi compose F compose phi inverse is smooth, right? We have psi prime compose psi prime psi inverse and um phi composed phi prime inverse are smooth. I hope you can convince yourself that the composition of smooth maps is smooth. Okay. Yeah, but these are all maps between Rn, so we don't even have to worry about that. Then note that the map psi prime compose psi inverse compose psi compose F compose phi inverse compose phi prime inverse is smooth, right? Because it's a composition of smooth maps. But now no, but see what happens, right? This psi prime and this psi give you identity. This phi inverse and this phi give you identity. So what you're left with is psi prime compose F compose phi prime inverse or phi inverse prime, whatever, it doesn't matter. So it seems as though like the choice of chart doesn't matter. Once it's smooth at one in one chart, it's smooth in all charts. Okay. Um, so this is psi inverse psi prime compose F compose phi prime inverse. Okay. Are there any questions about what smooth maps are? No. Okay. Let us now. I'm just seeing if I've missed anything. Okay. One thing of note is that one should be very careful about the domain and range of this map. I haven't written down the domain and range and stuff, but one should be careful about the domain and range. Same thing with the transition maps. I was just lazy. Okay. Um, Now, again, there's nothing special about smooth structures. We could also talk about, for example, analytic structures by replacing the word smooth everywhere by analytic. So we could require that the transition maps be analytic functions. If the charts were in CN, we could talk about complex manifolds. So um, we would look at when the transition maps are holomorphic. Okay. Um, so it when I talk about smooth manifolds, I mainly restrict myself to real smooth manifolds. Okay, let's now talk about in quantum mechanics. Let's now talk about um, one of the most quintessential manifolds in quantum mechanics. Okay, and that's the real projective space. Not the real. I mean, in manifold. I mean, in quantum mechanics, it's a complex projective space. But you know, let's look at projective space. Okay. So let V be a vector space. So it could be a real vector space or a complex vector space. Doesn't actually matter. Um, we could restrict ourselves to finite dimensions, but I'll see if we need to. So yeah, let V be a vector space. Then we define an equivalence on V as follows. We say V is equivalent to U if there is a lambda there's a non-zero scalar lambda such that V equals lambda U. Okay. Then the projective space of V is just the set of equivalence classes of elements. Okay. Does this definition make sense? So it's just saying that like you can scale a vector to you can just scale a vector. Um, so everything on the span of this vector um, is equivalent. So this is very important in quantum mechanics because, as we know, a global phase factor doesn't doesn't matter when we talk about measurements because in the Born rule it just cancels out. The probabilities cancel out. Well, sorry, the contribution from the scaling factor cancels out. Um, and this allows us to talk mainly about normalized states. Right? Um, so yeah, I mean, there's that. Um, I will outline in the problem sheet. Um, I will outline how to prove that this is in fact a manifold. Um, but for that, we'll actually first have to show that vector spaces are trivially manifolds. Um, actually, let's do that. Um, we show a vector space. Vector space V is a manifold. And what we're going to do here, the charts are going to be change of basis. Sorry, the charts are going to be is going to be a choice of basis. So a chart here will be a choice of basis. Now, why is this a chart? Why is this a homeomorphism? Right? That's very simple because this is a chart since a choice of basis since a choice of basis gives a linear map T from V into Rn, right? By just mapping V to its components. By mapping V to A1 to AN such that A1 V1 plus blah 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 AN Vn equals V. Here V1 up to Vn is the choice of basis. And in the topology we work with vector spaces, we know that linear maps are continuous. In fact, linear maps are smooth. One can now check that the transition maps are change of basis matrices, right? And those are just linear maps. So they're smooth. So vector spaces are smooth manifolds. Yeah. Um, this proof only works for the case of real vector spaces. You have to tweak this very slightly uh, to make it work for the complex case. Um, I will leave that as an exercise. I think it's a fun exercise. Okay. Um, Now one can now show that the dimension of this manifold is just the dimension of the vector space. Okay. Like in this case, the vector space dimension and the manifold dimension agree. Okay, so these are like some examples of manifolds and the main definitions of manifolds, smooth manifolds. Um, Next week we'll sorry, not next week, next meeting we'll talk about um tangent vectors. Um, we'll talk about tangent vectors and what the derivative of a smooth function is. Because we talked about smooth functions, we didn't talk about derivatives. Um, yeah, we somehow talked about a map being smooth without ever mentioning the word derivative, um, which is very funny. But yeah, we'll talk about um, like derivatives next meeting, but that definition is extremely the setup for that definition is a little out there, because the definition of a tangent vector is a little out there. Um, but yeah, we'll see that the best definition for a derivative is it acting on tangent vectors. Um, but we'll have to define what tangent vectors are for that. So I hope you're excited for next meeting. Um, are there any questions? Okay, if there are no questions, I will end the meeting here.